Imagine a scenario that, well, it basically keeps chief information officers awake at night. You are a senior executive at a Fortune 500 company.
Oh, the classic enterprise nightmare. I know where this is going.
Right, yeah. So your team has just spent like the last 18 months and frankly millions of dollars developing this brand new cutting edge customer facing web application.
Huge investment.
Massive. And this is the platform that is supposed to entirely redefine your market share, right? It's launch day. The marketing campaign has been flawless. The press releases are out. Millions of users are hitting the landing page. And then just total silence.
Ouch.
Yeah. The application completely crashes. Your war room is in absolute chaos. Software engineers are frantically running diagnostics, checking the code base line by line. But, and here's the kicker, the code is perfect.
That's always something else, isn't it?
Exactly. There are no bugs in the logic. The servers in the data center are powered on. The cooling systems are humming. The database is fully operational. So what happened? Why did this multi-million-dollar investment just evaporate?
Well, I mean, it almost certainly crashed because of a fundamental, almost invisible disconnect in how that beautifully written application communicates with the underlying network.
Right. Which brings us to the core of what we're doing today. Because to maintain a competitive edge in today's hyper-connected marketplace, it is not enough to just write good software or, buy really fast servers.
No, not at all. Corporate managers and IT leaders must understand the invisible bridge between the software you interact with and the network that carries it. If you don't, well, you end up in that war room.
Yeah, that is the ultimate nightmare scenario for any enterprise leader. And it happens far more often than people think, right?
All constantly. We see these massive outages in the news all the time. And the postmortem almost always reveals that this bridge you mentioned was fundamentally misunderstood by the architects who built the system.
Which brings us to our mission for this custom-tailored deep dive. Before we jump in, within the first 60 seconds here, I want to invite you to like, subscribe, and share this. If you want to ensure your organization always maintains a competitive edge and, well, avoids that launch day catastrophe, you are definitely in the right place.
Absolutely. And definitely check the description for access to additional corporate resources, diagrams, and some really great technical reading.
Yeah, the resources are key. For those following along with our overarching strategic analysis, this deep dive is based on materials specifically tailored for enterprise IT strategy. We're drawing from an extensive stack of educational materials, instructor guides, and textbook excerpts from Fundamentals of Communications and Networking, 3rd edition.
It's really all about equipping you with the strategic insights you need to lead effectively. Because understanding the technology is one thing, but translating that into business resilience is the real goal here.
Right. So let's unpack this. We are currently on the 6th episode of our 15-part arc. In our previous Deep Dive Chapter 5, for those tracking along, we covered the lower-level network and transport layers.
Yeah, the real plumbing.
Exactly. We talked about IP addressing, the massive transition from IPv4 to IPv6, and the mechanics of, connection-oriented communications. We were really down in the dirt looking at how raw packets find their way from point A to point B across the globe.
We were essentially studying the physical roads, the delivery trucks, and the traffic lights of the digital world.
I like that. But today, we have a new mission. We are jumping into Chapter 6. We are moving to the very top of the OSI model, the session, presentation, and application layers. We're going to explore how these upper layers dictate application architectures, how they manage network security, and, well, why a corporate manager desperately needs to understand them.
So if the lower layers are the roads and trucks, we need a new way to visualize these upper layers.
Right. How should we look at them?
Think of them as the shipping logistics, the language translation services, and the actual person signing for the package at the front desk.
Okay, I can see that.
Yeah, like the truck might arrive at the building perfectly on time, that is layer 3 and layer 4 doing their jobs, but if the person at the front desk doesn't speak the delivery driver's language or, refuses to sign the clipboard, the package never reaches the recipient. The business transaction fails.
That makes perfect sense. So let's start right at the point of contact. The human network interface, officially known in the OSI model as Layer 7, the application layer.
Right, the very top.
The textbook explicitly calls this out as unique because it is generally the only layer in the entire OSI model that interacts directly with the human being.
Exactly. It serves as the primary interface for application software to interact with networks. Because of this, you will often hear network engineers refer to it as the user interface layer.
But the source material makes a really specific, almost counterintuitive distinction here that I want to challenge. It states that the application layer is not the user application itself.
Right. It's a subtle but crucial difference.
Because, I mean, if I am sitting at my desk clicking around on a web browser like Chrome or Edge, isn't that my application? How is Chrome not layer 7?
That is probably the most common point of confusion for anyone stepping into network architecture. What the OSI model calls an application is not the user application sitting on your desktop.
Really?
Yeah, Chrome, Microsoft Word, your company's proprietary inventory software, those are user applications running on your operating system. They actually sit outside the OSI model entirely.
Oh, wow. Okay, so what does layer 7 actually do then?
Layer 7 provides the services for those user applications. Every single process to exchange a message with another computer generally starts with a layer 7 software call. It's the service the application uses to make a request to the network.
Let me try a business analogy to clarify this for the corporate managers listening. Imagine you are a manager taking a client out to a fancy restaurant. You, the human, are using the menu to figure out what you want.
Okay, I'm tracking.
The web browser is the restaurant setting the table, the menu, the ambient lighting. But the application layer, layer 7, isn't the menu or the food. Layer 7 is the waiter.
Yes, that works perfectly. The waiter is the intermediary between your desires and the kitchen's execution.
You don't just walk into the kitchen, push past the chefs, and start grabbing ingredients, right?
Yeah, I hope not.
Right. You interface with the waiter, you tell the waiter what you want, and the waiter translates that request into a standard format and carries that order to the kitchen. The waiter is the software entry point for sending messages.
And just like a waiter has specific procedures for placing an order, maybe they have to write it down on a specific ticket or punch it into a point-of-sale terminal layer. Layer 7 uses specific protocols to make those software calls to the network.
The textbook highlights a few of these specific Layer 7 protocols. One that immediately jumped out to me is SIP, or Session Initiation Protocol.
Oh, SIP is huge.
Right. This comes up constantly in enterprise IT budget meetings when we talk about unified communications.
Yes. Unified Communications, or UC, is a massive investment area for enterprises right now. It is the integration of voice telephony, video conferencing, presence information, knowing if someone is away from their desk, and instant messaging all into a single cohesive platform.
And SIP is what makes that happen.
SIP is the critical Layer 7 protocol that enables all of that, yeah.
How does SIP actually function as the waiter in that scenario?
So when you click a button in your UC application to start a video call with a remote engineering team, your click is the customer giving the order.
Okay.
SIP is the waiter taking that specific request to the network to negotiate and initiate the session. It tells the network, I have a user here who wants to start a real-time two-way video and audio stream with these specific IP addresses. It sets up all the parameters for the call.
Another major Layer 7 protocol, of course, is HTTP, which handles the requests for web browsing.
Exactly. HTTP is the waiter for the web.
But why does a non-technical manager need to care about the waiter? I mean, if I am a director of operations, why should I care about SIP or HTTP as long as my video call connects?
You need to care because every online interaction begins right here. And understanding this layer is how you troubleshoot systemic business failures.
Give me an example.
Well, if Layer 7 fails, if the waiter drops the order on the way to the kitchen, the user experiences total system failure. The network could be perfectly optimized, the fiber optic cables could be pristine, the servers running at lightning speed. But if the application layer cannot properly interface with the user's software, the business grinds to a halt.
Ah, so it's just like the opening hook, the application crashes, the kitchen is fully staffed, but no orders are coming in.
Precisely. You have to know where the breakdown is happening to fix it.
So if the waiter takes my order successfully, what happens next? The waiter needs to make sure the kitchen actually understands what was ordered. That brings us down a step in the OSI model to Layer 6, the presentation layer.
Yes, moving down the stack.
I like to think of this as the universal translator.
That's a great way to describe it. The presentation layer provides the critical interface between the application layer we just discussed and the session layer beneath it. Its primary defining job is syntax translation.
Syntax translation, can you break down the actual mechanics of what that means?
Sure. On the sending computer, Layer 6 is responsible for formatting and coding high-level data that comes from applications into a form that is acceptable for transmitting on the network.
Okay, so it preps it for the wire.
Right. It takes the abstract concept of a document or a spreadsheet and makes the data presentable for the network cables. Then on the receiving computer, it does the exact reverse. It translates the raw data it receives back into a format acceptable for the receiving application layer.
The textbook explicitly cites ASCII here, the American Standard Code for Information Interchange.
ASCII is the classic textbook example, yeah. When you type characters into a web form, the physical network cables don't understand the letter A or the letter B.
Right. They just see voltage.
Exactly. They only understand electrical pulses representing binary ones and zeros. Layer 6 ensures that the character data is converted into standard formats like ASCII so the underlying systems can process it.
Does it do anything else besides character translation?
Oh yeah. It handles character encoding, it can handle data compression to save bandwidth, and crucially for modern business, it handles encryption and decryption at this stage.
Here's where I want to push back a little, though. We talk about ASCII, but in a modern enterprise, software feels so standardized now. We all use web APIs, we use JSON, everything is built for the cloud. Is a dedicated translation layer really still that relevant?
It is actually more relevant now than ever.
Really? Why?
Because of hardware fragmentation. 30 years ago, a company might have purchased identical desktop computers for every single employee. The hardware architecture was exactly the same.
True. Everyone had the exact same beige box.
Right. Today, look at the reality of a modern enterprise ecosystem. You have a sales representative accessing the CRM on an iOS smartphone. You have a graphic designer uploading assets from a Mac running an ARM-based processor.
And an accountant running heavy macros on a Windows PC with an Intel chip?
Exactly. And warehouse workers scanning inventory on custom Android tablets.
And all of those different operating systems and microchips process memory differently, don't they?
They absolutely do. An integer, like a basic number in a database, might be structured completely differently in the physical memory of a Mac compared to a PC.
So what happens without layer 6?
If the Mac just sent its raw, native binary string across the network to a Windows server, without the presentation layer acting as that universal translator, the Windows server would read the binary backwards or misinterpret the spacing. You would get complete data corruption.
Oh, wow.
Yeah, the number 1000 might be read as 1 million.
That is a terrifying thought for a financial institution.
Layer 6 ensures that regardless of the hardware, the operating system, or the silicon architecture, the data remains presentable, usable, and maintains absolute integrity across complex enterprise networks. It is what allows the iOS device to talk seamlessly to the legacy Linux server.
It truly is the United Nations translator of the network. So we have our order from the waiter. It has been translated into a universal language by the presentation layer. Now we hit layer 5, the session layer.
Yes.
The textbook refers to this layer managing active dialogues, which, to be honest, sounds a bit abstract.
Layer 5 is fascinating, actually, because it introduces the concept of time and turn-taking into the network. This layer sets up, manages, and terminates connections between applications on source and destination computers.
Wait, I am confused. Didn't we establish in our previous deep dive on Chapter 5 that TCP, the transmission control protocol at layer 4, handles connections? Why do we need another layer for connections?
That is a great distinction to make. TCP at the transport layer is about establishing a reliable end-to-end physical data stream.
It just keeps the pipe open.
Exactly.
Yeah.
It ensures that packet number 1 arrives before packet number 2. But the session layer is higher up. It is managing the dialogue between the applications themselves.
So TCP handles the pipe, but session handles the conversation.
Right. TCP keeps the connection from dropping, but the session layer determines how the entities on either end of the pipe actually speak to one another.
The source mentions different communication modes managed here. Full duplex and half duplex. Let's explore the mechanics of those.
In full duplex mode, both ends of a connection can communicate simultaneously. Think of it like a standard cellular telephone call. Both people can talk and listen at the exact same time. The dialogue is free-flowing.
And half duplex is different.
Yeah, half duplex is where both ends can communicate, but only one at a time.
Like walkie-talkies, you have to press the button, say over, and let go before the other person can speak.
Exactly like that.
But why would any modern enterprise system use half duplex? It seems so archaic. We all have high-speed internet now.
It might seem archaic, but it is heavily utilized in specific enterprise environments to manage network collisions and legacy systems.
Like where?
Well, if you have a highly congested network, or you are running specific types of radio frequency inventory scanners in a massive warehouse, half duplex ensures that the central server isn't completely overwhelmed by thousands of devices screaming at the same time.
So it forces them to take turns?
Right. The session layer manages who has the token to speak in a half duplex scenario. It tells the scanner, okay, it's your turn, transmit your barcode data, and tells everyone else to wait. A common protocol that operates explicitly at layer 5 to manage this is RPC, or Remote Procedure Call.
Let me bring this back to a managerial analogy. If layer 7 is the waiter and layer 6 is the translator, layer 5 is the moderator of an intense corporate boardroom meeting.
I like that.
The moderator doesn't care about the language being spoken. That is the translator's job. And they don't care about the actual topic of the meeting. That is the waiter's job. The moderator just keeps track of whose turn it is to speak, ensures the active dialogue remains focused until the business transaction is totally complete, and then formally adjourns the meeting so everyone can disconnect and go home.
That captures the essence of layer 5 perfectly. If the moderator fails, people talk over each other, the meeting descends into chaos, and the transaction is never finalized.
Understanding these top 3 layers, application, presentation, and session, gives us the theoretical foundation. But how do these layers physically manifest in the software solutions that businesses actually buy, build, and deploy?
This is a huge pivot.
Right. This leads us into a critical area for operations executives, aligning application architectures with business strategy.
This is where the academic theory hits the balance sheet for corporate managers. The textbook introduces a fundamental, unbreakable rule for IT managers. Never adopt a technical solution and then figure out how to apply it to a problem.
We call that shiny object syndrome in the business world.
Exactly. You are at an industry conference, you see a vendor demo for a flashy new AI-driven, blockchain-enabled cloud platform. It looks incredible.
So you buy it.
Right. You buy a $1 million enterprise license, bring it back to your team, and ask, okay, what can we use this for? That is a recipe for operational disaster and wasted capital.
It really is. So what's the rule?
The rule is absolute. Always start with a business problem. Then, identify a business solution. And only then do you identify a technical solution that enables that specific business solution.
It sounds like common sense, but it gets violated constantly in the pursuit of modernization. So let's dig into the technical functions, specifically application architectures.
Okay, let's do it.
The source defines architecture as the processing logic that carries out computations on application data. Choosing the wrong architecture doesn't just waste money. It can cripple a network's performance.
Let's trace the evolution of these architectures, starting with the original, host-based architecture.
When we say host-based, we are talking about massive legacy mainframes, right? The giant computers filling entire rooms in the 1970s.
Historically, yes, mainframes. In a host-based architecture, the server, the host, does absolutely everything. It stores the database, it processes the business logic, and it even formats the visual interface.
So what does the user actually have on their desk?
The user's device is just a dumb terminal. Literally just a screen and a keyboard with almost no processing power of its own. It simply displays what the host tells it to display.
Why would a business use that? What are the benefits and drawbacks?
The primary drawback is that it is a single point of failure. If the central host goes down, the entire company stops working. Every single terminal goes black.
And it must be hard to scale.
Incredibly difficult and expensive to expand. If you hire 50 new employees, you might have to upgrade the central mainframe's processor, which is a massive, multi-million-dollar capital expenditure.
But there must be a benefit. Otherwise, it wouldn't have been the standard for decades.
The benefits are superior. Centralized security controls and incredibly simple software deployment.
How so?
If you need to update the inventory software, you update it once on the mainframe, and instantly, every single terminal in the company is running the new version. There is no patching thousands of individual laptops.
That makes sense. But as the hardware evolved and personal computers became cheaper, we moved to client-based architecture.
Right. This was the immediate response to the limitations of the mainframe. In a client-based architecture, the workstation on the user's desk, the client PC, does the heavy lifting. The server in the back room essentially just becomes a shared hard drive for file storage.
The benefit there is obvious. You leverage all that cheap processing power on the user's desks, and you take the expensive computational load off the central server.
Yes, but the textbook warns that this architecture has a fatal flaw regarding something called network I/O.
I have to admit, as a manager, I hear network I/O thrown around, but I need you to break down exactly what that means mechanically.
Sure. I/O stands for input-output. It refers to the physical transmission of data across the network cables. Let's look at the mechanics. Imagine your company has a 10 gigabyte database of customer records stored on the server.
Okay, got it.
You are sitting at your client-based PC, and you want to search for one specific customer named John Smith.
Simple enough.
In a client-based architecture, because all the processing logic lives on your PC has to perform the search. But the database is on the server. So your PC requests the database. The server sends the entire 10 GB file across the network cable to your PC.
Wait, really? The whole thing?
Yes, your PC receives all 10 gigabytes, searches through it locally, finds John Smith, displays his file to you, and then just discards the other 9.99 gigabytes of data.
That is incredibly inefficient. If 50 employees run a search at the same time, they are dragging 500 gigabytes of data across the network wires just to find 50 names?
Precisely. That is excessive network I/O. It causes massive congestion. Performance becomes entirely tied to network bandwidth. It is highly unscalable for data-intensive applications.
Which naturally leads us to the evolution of client-server architecture. How does this solve the I/O bottleneck?
Client-server got smarter by separating the processing functions. The server holds the data and performs the data-intensive processing like running the database search locally on its own hardware. The client PC handles the user interface and the application logic.
Let's use a real-world scenario from the instructor guides to illustrate this. Let's take Arroyo Shoes, a fictitious enterprise shoe manufacturer located in the United States. They are upgrading their internal inventory system in the late 1990s.
Okay, great example. If Arroyo Shoes uses a client-server architecture, here is how the search changes. The employee searches for size 10 running shoes.
Right.
The client PC sends a tiny text request across the network to the server. The server receives the request, queries its own database internally, finds the 20 matching shoes, and sends only those 20 text records back across the network to the client PC.
Oh, so the network I/O is perfectly balanced. You aren't dragging the whole database across the wire.
Exactly. The benefit is optimized network traffic. The drawback, however, is complexity. It is much more difficult to code and deploy.
Because you're managing two systems.
Yeah, your software engineering team has to write two entirely separate pieces of software, a client application for the user's PCs, and a server application for the data center, and keep them perfectly in sync during every update.
But client-server isn't enough for today's hyperscale businesses. I mean, what if Arroyo Shoes launches a massive direct-to-consumer e-commerce website today, and they run a commercial during the Super Bowl? Millions of hits in a matter of minutes. A standard client-server setup would melt.
Oh, it absolutely would melt down. That brings us to cloud computing and N-tier architecture. N stands for any number of tiers. This is where the application server, the app server, was introduced as a distinct middle layer.
Walk me through the mechanics of an N-tier setup for Arroyo Shoes during that Super Bowl spike.
Instead of two tiers, client and server, you distribute the load across many specialized servers. First, you have the user's web browser, the client tier. The client sends a request to a web server tier.
What does a web server do?
The web server's only job is to handle the HTTP requests and display the images of the shoes. But the web server doesn't know how to process a credit card. So it passes the transaction to the application server tier, which holds the business logic, calculating sales tax, applying discount codes, processing shipping.
And then?
Finally, the application server queries the database server tier, which strictly handles data storage and retrieval.
You have atomized the functions. What is the strategic benefit of doing that?
Ultimate scalability. If the Super Bowl commercial drives millions of people to look at pictures of shoes, the web server tier will get overwhelmed, right?
Yeah.
In an N-tier cloud architecture, the IT manager can instantly spin up 20 more virtual web servers to handle the incoming traffic without having to touch or replicate the application servers or the database. You scale only the specific tier that is under stress.
That is brilliant, but there has to be a catch. What is the business drawback to N-tier?
The drawback is operational complexity and disaster recovery. When your application is spread across dozens of virtual servers in multiple geographic regions, tracking down a failure is incredibly difficult.
I can imagine.
Yeah. If a transaction fails, did it fail at the load balancer, the web server, the app server, or the database? Disaster recovery planning becomes a nightmare because there are so many moving, interdependent parts.
The textbook introduces one more architecture that seems entirely different from the rest: peer-to-peer, or P2P.
P2P completely abandons the centralized server model. There is no central host. Every single client on the network acts as both a consumer and a provider of resources.
Let's use another scenario from our sources. Highbrow education, a large, sprawling university campus. Why would they utilize P2P?
Universities often use P2P for distributing large academic files or datasets. If a professor needs to share a 50-gigabyte video lecture with 300 students, putting it on one central campus server would crash that server when everyone tries to download it at once.
Right, the bandwidth would just bottleneck.
Exactly. In a P2P network, The first few students download pieces of the file, and then their laptops start sharing those pieces with other students' laptops.
The load is distributed automatically among the users?
Exactly. The benefits are significant. It is highly fault-tolerant. If 10 students close their laptops, the network survives because the data is distributed elsewhere. Contention for a central resource is low, and it is infinitely scalable with no central authority. The more users you add, the more bandwidth the network actually has.
But the drawback has to be security, right?
Oh, it is an absolute security nightmare for a corporate enterprise. Because data is scattered across thousands of uncontrolled endpoints, securing confidentiality is almost impossible. Furthermore, conflict resolution, deciding which version of a file is the most recent, has to be negotiated among peers rather than dictated by a central trusted authority.
I want to ask you a strategic question that ties this back to the business rule we started with. We have all these modern, infinitely scalable cloud and N-tier architectures available today. Why on earth would a modern business intentionally choose to regress and use an older architecture, like a host-based setup?
That is the exact question a CIO should be asking. It all comes back to risk appetite and the specific business problem. Let's say your business is a highly classified government defense contractor or a financial institution executing ultra-sensitive algorithmic trades.
Okay, very high stakes.
Your primary business problem is not scalability. You aren't running Super Bowl ads. Your primary business problem is extreme security and data sovereignty.
You cannot afford for a single byte of data to leave the building.
Exactly. A modern host-based architecture, often deployed today as virtual desktop infrastructure, or VDI, provides unparalleled security controls.
Because the data isn't on the local machine.
Right. The user has a SYN client on their desk. They can see the data on their screen, but the actual data never leaves the central lockdown server room. You intentionally sacrifice the agility and scalability of the cloud to guarantee that an employee cannot physically download a proprietary database onto a USB drive. The business problem dictates the architecture.
That is a phenomenal insight, aligning the strategy before touching the technology. Now that we understand the architectures, let's explore how these systems actually route traffic. This brings us to Section 5 of the source material: network ports, sockets, and the denial principle.
A very technical but very crucial topic.
Right. We know the architecture is spread out, but how does an application server know how to find the database server?
This is where we get into the literal mechanics of addressing at the application layer. When a client sends a request to a server, it doesn't just send it to the server's IP address. An IP address only gets the packet to the physical machine. But a modern server is running dozens of different services simultaneously. It might be running a web server, an email server, and a file transfer server all at the same time.
So how does the network know which specific service the packet is meant for?
It uses a port. Think of the server's IP address as the street address of a large high-rise apartment building. A port is the specific apartment number.
Ah, I like that.
It is a logical construct, a number ranging from 0 to 65,535 that tells the server exactly what type of service the incoming client is requesting.
So if the packet arrives at the building, it checks the port number to know which door to knock on. But what is a socket? The text distinguishes between the two.
This is a crucial mechanical distinction. A port is just a numbered door. A socket is an instance of a software service that is actively bound to that port, listening for traffic.
So if the port is the apartment door, the socket is the person sitting inside the apartment, actively listening for someone to knock.
Precisely. If a packet arrives at port 80, but there is no socket listening, meaning the web server software is turned off, the packet just hits a closed door and is dropped by the operating system.
The source outlines several essential enterprise ports that every IT manager needs to know by heart, because these are the most common doors used in corporate infrastructure. Let's walk through a day in the life of an IT manager monitoring these doors. First, ports 80 and 443.
These are the busiest doors in the building. Port 80 is designated for HTTP, standard unencrypted web browsing. Port 443 is HTTPS, the secure encrypted version of web traffic.
So everyone needs these open.
If you are running an e-commerce site, your socket on port 443 better be highly optimized and listening constantly.
Next, the IT manager sees traffic hitting ports 20 and 21. What is happening there?
That is FTP, or File Transfer Protocol. This is used for moving large data files from one computer to another over a reliable TCP connection. Port 21 is used to establish the connection and send the control commands like authenticate user or list directory, and port 20 is the channel where the actual data transfer takes place.
What if suddenly the firewall logs show a massive spike in external traffic trying to hit port 22? Why should the IT manager be alarmed?
Port 22 is SSH, or Secure Shell, and SFTP, Secure FTP. This port allows secure, encrypted remote access to the command line of a device. It is how network administrators log into servers remotely to manage them.
Oh, so if someone is hitting that,
If you see external unknown IP addresses hammering port 22, it means attackers are actively trying to guess your administrator passwords to gain total control of your infrastructure.
what about port 53?
Port 53 is DNS, the domain name system. This is the directory service of the internet. It translates human-readable, fully qualified domain names like www.yourcompany.com- into the numeric IP addresses that routers need. Without DNS functioning on port 53, users would have to memorize the IP address of every website they want to visit.
That would be a nightmare. The text also mentions port 161.
Port 161 is SNMP, the Simple Network Management Protocol. This is a UDP-based service used heavily by network operation centers. It allows central management servers to poll routers, switches, and servers to collect performance metrics.
Like checking their health.
Yeah. What is your CPU usage? Is your cooling fan operating? It is the heartbeat monitor of the network.
Finally, there is TFTP, which stands for Trivial File Transfer Protocol. The word trivial makes it sound harmless, but is it?
It is anything but harmless if exposed. TFTP is a lightweight, connectionless version of FTP that uses UDP. It has absolutely no authentication and no security. It is designed to be fast and simple.
Where is it used then?
It is often used internally by hardware devices. For example, cable companies use TFTP to automatically push configuration files to your physical cable modem when you power it on. But if a corporate manager leaves TFTP open to the public internet, anyone can download your configuration files or push malicious firmware directly to your devices.
Which brings us to this strategic security takeaway for the enterprise regarding all these ports. A server has over 65,000 potential ports. How does an organization possibly manage that risk?
The most critical takeaway here is the deny-all principle. Historically, network engineers would set up a server and try to manually identify and block the dangerous ports, one by one. They would say, let's block port 22, let's block TFTP.
But humans make mistakes. They will forget a port, leave an obscure door unlocked, and an attacker will eventually scan the building, find it, and walk right in.
Exactly. Corporate policy must dictate the denial principle. You configure your firewalls and servers to block absolutely everything by default. Every single door is bricked over.
And then what?
Then, and only then, do you explicitly open the specific ports that are strictly necessary for your documented business operations.
It is the concept of least privilege applied to network routing. If you are deploying a public-facing web server, you open port 443 for HTTPS, and you leave the other 65,534 ports permanently closed.
That is the only defensible posture in a modern threat landscape.
Let's take all of this theory, the upper layers, the complex N-tier architectures, the specific ports, and bring it together to understand the modern threat landscape. The ultimate manifestation of these upper OSI layers is the World Wide Web.
The web is the absolute workhorse of modern global business, and at its core is the HTTP request and response process. We mentioned HTTP earlier, but it is worth detailing the mechanics of how it actually moves data because attackers exploit these specific mechanisms.
The textbook specifically points out the critical difference between HTTP GET and HTTP POST requests. How do they function differently?
When your browser wants to retrieve and render a web page, it initiates an HTTP GET request to the server. It's essentially asking, please give me this resource. The parameters of the request are appended directly to the URL, which means they are visible in the browser's address bar.
But what if I am filling out a login form with a username and password, or submitting credit card data? I certainly don't want that visible in the URL.
Exactly. That is when your browser uses an HTTP POST request. POST submits data to a resource through the web server, enclosing the data in the body of the HTTP request, completely separate from the URL. This triggers server-side processing, like querying a database to verify a password.
This brings us to the dark side of the network. Because these upper layers, especially application and presentation, interact so closely with user logic and network ports, they are prime targets for sophisticated attacks. Security at layer 7 is radically different than security at layer 3, isn't it?
It is a completely different paradigm. At layer 3, the network layer, you are dealing with infrastructure attacks, IP spoofing, manipulating routing tables, flooding the pipe with junk data. But at the application layer, the attacks are much more insidious. Attackers are targeting the software logic itself. More importantly, they are targeting the human user.
Let's discuss the specific application layer threats outlined in the source material. First, denial of service, or DOS. How does an application layer DOS differ from just flooding the network?
A standard network DOS just clogs the pipes. An application layer DOS is much smarter. It occurs when an attacker intentionally consumes the specific resources on a target computer like its CPU or memory by sending complex, legitimate-looking Layer 7 requests.
Can you give me an example of how that works mechanically?
Let's go back to our N-tier e-commerce site. An attacker might use a script to send thousands of HTTP POST requests to the search bar, asking the server to run a highly complex, resource-intensive database query.
Ah,
The network pipe isn't full, but the database server's CPU maxes out at 100%, trying to process all those fake searches. The goal is to overwhelm the system from the inside out, preventing normal, legitimate customers from executing transactions.
next on the list are Trojan horses.
A Trojan horse is a type of malware that is disguised as a useful program. It might look like a legitimate PDF invoice or a software update for your browser. It relies heavily on human gullibility.
So the user opens the door.
Yes, the user willingly clicks the file, and while it might open a document to maintain the illusion, it secretly installs a backdoor on the system.
Which connects directly to the concept of botnets. I want to highlight a common misconception here that was specifically targeted in the textbook quiz, because corporate managers often misuse this term. People often associate botnets entirely with ransomware.
Yeah, that is a very common managerial misconception. A botnet is a vast network of compromised computers, often millions of devices infected via those Trojans we just discussed. These devices, called zombies, are controlled remotely by a central attacker, known as a bot herder.
So while they could be used to deploy ransomware, what is their primary fundamental purpose?
Botnets are most closely and fundamentally associated with distributed denial of service, or DDoS attacks. The attacker uses the botnet command and control infrastructure to launch a coordinated DOS attack from millions of different IP addresses simultaneously.
How does that look from the perspective of the victim's server?
It is devastating. If one computer attacked you, you block its IP address. But in a DDoS attack, you're receiving malicious requests from smart refrigerators, compromised corporate laptops, and insecure webcams all over the globe, all at the exact same second. It is incredibly difficult to defend against because the traffic looks legitimate and comes from everywhere.
We also need to talk about Telnet. We mentioned SSH earlier as the secure way to access a remote terminal. Why is Telnet considered a massive, unacceptable security risk at this layer?
Telnet is an ancient protocol used for remote terminal access. The fatal mechanical flaw with Telnet is that it operates before modern presentation layer encryption was standardized. It sends all data, including administrative usernames and passwords, across the network in clear text.
So if a manager is using Telnet to log into a core router, and an attacker is sitting anywhere on that network pathway,
The attacker can simply open a network sniffing tool, like Wireshark, capture the packets, and read the administrator's password as plain text on their screen. There is zero cryptographic protection. This is why SSH on port 22, which encrypts the entire session at the presentation layer, entirely replaced Telnet as the standard for secure remote management. If you have Telnet running anywhere in your enterprise today, you are inviting a breach.
what really stands out to me here, the big realization from analyzing these upper layers, is that application security isn't just about configuring firewalls or buying expensive intrusion detection systems. It is fundamentally about anticipating human behavior.
Exactly, because Layer 7 is the only layer that interacts directly with the users.
Right. It is the user who is going to get tricked into clicking the Trojan horse. It is the user who might try to use Telnet because it's the command they learned 20 years ago. As a corporate manager, your security perimeter isn't just the firewall at the edge of the network. Your perimeter is the psychology of your employees.
That is a profound strategic way to look at it. You cannot secure the application layer with technology alone. You have to secure it through continuous education, stringent corporate policies, and by architecting systems that limit the damage a user can accidentally cause.
Well, this has been an incredibly eye-opening journey up the OSI stack. To recap our primary managerial takeaway for today, the upper layers of the OSI model, the session, presentation, and application layers, are where high-level business strategy literally becomes network reality. A misconfigured application architecture that causes massive network I/O or a single unnecessary open port on a public server can completely compromise enterprise infrastructure.
It really can.
Think back to our opening hook, that crashing multi-million-dollar web application on launch day. It wasn't the software code that failed. It was the failure of the IT architects to understand how the application interfaces with the network under load. It was a fundamental failure at the application and session layers.
The stakes for corporate leaders couldn't be higher, and understanding this bridge is essential. And this perfectly sets the stage for where we go next, because next time, in Chapter 7, we're going to drop back down the protocol stack to explore Layer 2 networking.
Layer 2, the data link layer.
Yes, we will understand how physical endpoints actually connect and communicate on the local area network. We will dissect why mastering Ethernet LAN topologies in virtual LANs VLANs is the next crucial piece of the technical puzzle. We have talked about the high-level application strategy today. Next time, we will look at how to physically and logically segment the network hardware to safely support that strategy.
I am looking forward to it. As a reminder, please check the description provided with this deep dive for direct access to resource links, network diagrams, and the technical reading materials that form the foundation of today's discussion. If you found this strategic analysis valuable, you will definitely want to explore the other resources available, including our modules designed for continuous professional education. We also highly recommend our other deep dive series, such as the Digital Forensics Analyses and the Network Systems Security series.
And as we close today's session, I want to leave you with a final reflective question to mull over as you review your own corporate infrastructure. As modern N-tier and cloud architectures continue to distribute our data globally across dozens of virtualized servers and microservices, how will the traditional boundaries of sessions and ports evolve to protect information that never sits in just one physical place?
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.